Hi everyone, this is our submission to the Chainlink Constellation Hackathon for our project titled Cross-Link Private Supply. So what we want to achieve in this project is a privacy-enabled supply chain scenario where the buyer and the seller or any other trade entities may live on the different chains. And what we do in this project is we enable cross-chain communication through CCIP, and we also use CIRCOM's ZK proofs, both the solidity verifier contract generated from it and the proving mechanism itself to ensure that the supply chain scenario is private. So in this particular instance, we have a buyer who wants to buy some amount of something from the seller. And there are two things that we need to keep private. First is how much the buyer is trying to buy. So the buyer doesn't want to have everyone know on chain what their query is. And then the seller does not want to reveal their supply of the commodity. So given some query that the seller can decrypt, the seller is going to generate a ZK proof that will either be returned yes or no, depending on whether the seller can meet the supply request. So without further ado, let us get started. So this is the deployed seller and the buyer and the seller contract on BSC testnet and the Ethereum testnet. And we can first start by generating a public key. So this public key is used to sign the amount of the request that the buyer will make. So we can first, so we're on the BSC chain, we can set the CIRCOM key on the network, which will send a transaction just to the BSC contract. And then we can then send a transaction which will trigger the BSC contract, the buyer contract, to send the CCIP communication to the seller contract. So it says we have it just went through. So we will send another one. And it should go through pretty quickly. We can go back and check on the events to see if it's going through on the Chainlink network. And then the seller can then, let's first switch to the seller's network, get their Ethereum public key. So this public key is also used to encrypt the request that the buyer would make. This allows that only the buyer and the seller can understand what the contents of the query is. So we can again share this key. Now this will trigger the seller contract on the Ethereum network to so we can see the addresses match to the BSC network so that the smart contract knows their public key. And then we can sign some amount. Let's say the buyer wants to buy 12 something. Then we can sign it using our circuit private key that only the buyer knows. And then we have this signed amount. So we can then encrypt this by using the Ethereum public key of the seller. And we have this encrypted request that can go to the seller and only the seller can decrypt. So let's say we sent it. And then the seller can decrypt it. So this will send a request on the MetaMask to use their private key to decrypt this. And we get the same request back. And then for step 6, now we finally need to generate the proof. So using the signed amount, let's paste it in here. And then the known public keys of the CIRCOM public keys of the buyer. We can then prove that we can meet this demand that we actually don't know of that with this supply. So right now it says the amount, but that's because we decrypt it. So when it's encrypted, it doesn't actually say any of that stuff. And we add some random salt, let's see, and we generate the proof. So this will generate this proof that can be then sent to the buyers. And then the buyer can then verify this using a verifier contract generated by CIRCOM along with the circuit. So we can then send the proof. So we're still on the Sepolia network. We will send this proof. And we can then, so that just went through. So we can verify that these events just happened. So we have our 2 sends from the Ethereum contract. And then we have our 2 sends from the BSC contract. So the second one was the cross-chain contract or the transaction. So let's go back, copy this, and look it up on the Chainlink Network Explorer. So it's committed. We can come back to this, and hopefully we can see that it succeeded. So in the meantime, we can also show that the proof can indeed be verified using our testing script. So we have this testing script here. So it uses the buyer's contract address to instantiate one and instantiate the contract, and then we call this verify proof, which is the endpoint that's called for verifying, and then we will log in the terminal whether it returned true or false. So first we can paste the new proof here. So we just pasted this and saved it. We will now run this on using our testing scripts. So we will test buyer. This will run the script. So we can again see it's running the thing with the BSC RPC URL. And there's a lot of outputs. But what we were looking for is this line right here. So this tells us that the proof is indeed returning true. And that is because the seller has 20 something, I think. Yeah, like 29 supply, and then the buyer asks for 12. So we can see now the transaction was blessed. We will skip to where it is actually confirmed and successful. In the meantime, both of our contracts have one link token, or actually not anymore. It had one, but we used it. But they're loaded with the link tokens to facilitate the transaction. And now we see that our transaction did indeed go through. And then if we go into the events, we should see, it received I believe this was the public key that was sent public key that was sent to the Ethereum contract. So this shows that our project was able to successfully use the CCIP protocol for enabling cross-chain communication, as well as using zero-knowledge proofs using CIRCOM and Snark.js library. This concludes our presentation on our hackathon project, and I hope you guys were all interested. Thank you.